Okay, last video here. Section 10.3. We're going to do some hypothesis tests for means, but this time we're not assuming that we know the population standard deviation, so we're going to look at what we do if we don't know the population standard deviation instead, which this is much more common. Okay, usually we don't know the population standard deviation if we're testing for a mean. So the first big change we have to make is we have to use a different test statistic. Okay, the formula is very similar, but this time we're going to end up with a t-test statistic using the student's t-distribution instead of the normal distribution with the z. So if we don't know the population standard deviation and the central limit theorem is still in effect, we still need that here, so we still need a sample size of at least 30, or to know our population data is approximately normal. Then we can do a hypothesis test using a t-test statistic. Okay? So this formula is very similar to the z-test statistic. Remember, there are a few things first to remember: that mu is going to come from the null hypothesis, and it's going to be our number we're assuming to be true. X bar is going to come from the sample data, so that helps us keep from getting those two means confused with each other. And then the other difference here is that this S is not population standard deviation, that's sigma, but this is the standard deviation of our sample data. Okay? We've got to collect sample data anyway, so we can just calculate the sample standard deviation and then we'll use that in our formula instead of sigma. But because we're doing that, we have to adjust a little bit by using the student's t-distribution instead of the normal distribution. Okay? So that's one of our big differences here. Okay? So with that said, let's look at one other thing we need to know for being able to deal with these t-test statistics. Okay? Remember, in order to look up a t in the t-table, we need two pieces of information. We need to know something about the area and the tails of our distribution we're working with, and we also need degrees of freedom. So where do we get degrees of freedom? Well, it turns out it's the same as we saw when we were dealing with confidence intervals. To get degrees of freedom here, we're going to do the sample size minus 1. Okay, so whatever the sample size is, we subtract 1 from that, and that tells us what number of degrees of freedom to use. Okay? So that slight change in the formula is one of the big pieces that we have to deal with. Okay? There's one other thing we have to deal with, and it's really just in this class. You don't necessarily have to deal with this out in real life. If you're doing t-test statistics, you can still find a p-value. But since our t-tables are not very detailed, we have to use a different method to come up with our conclusion. We don't really have the ability to find a p-value because our t-tables are just not that detailed. So instead of using p-values, we use another method. Okay, it's really just, we're doing the same thing, it's just another way to think about it. Okay? And this other method we're going to use is called rejection regions. Okay, we're going to set up something called a rejection region instead of calculating a p-value. All right, so if we look at our rule here, the idea is we're going to come up with some critical t-value that's going to tell us where our rejection region starts. And then we will say, well, if our test statistic falls in a certain relationship to that critical t, that tells us what to do. So if we're doing a left-tailed test, okay, so on this side, these are the critical values. So these t-values on the right side, we're just going to look those up in the t-table. And then the t-values on the other side, okay, these are our test statistic t's. So these t's are coming from our formula. Okay. So for a left-tailed test, look at our inequality there. It points to the left, right? So in order to reject the null hypothesis, our t-test statistic needs to be less than or equal to our critical t. If we're doing a right-tailed test, our test statistic needs to be greater than or equal to our critical t. And if we're doing a two-tailed test, this one's a little confusing the way it's worded here, but it says the absolute value of our t, our test statistic, needs to be greater than our critical t. That one we'll look at in more detail in just a second. Let's look at a picture of each one of these. I think the picture really is more helpful than looking at the rules here, so let's take a look at what these look like. So we're gonna, well, this says z. Okay, let's change this to t. This is negative t sub alpha. Okay. So the idea here is if we're doing a left-tailed test, we're going to find our negative critical t. And then if our test statistic falls anywhere over here to the left, then we reject the null hypothesis. Right? If it falls in the left tail for a left-tailed test. Right? So that hopefully that makes sense. If our test statistic is over in the left tail for a left-tailed test, that means we reject the null hypothesis. If we're doing a right-tailed test, it's just opposite. Okay? Our critical t will be over on the right side. And if our test statistic falls somewhere in this right tail that's greater than that critical t, then we reject the null hypothesis. Okay? And if we're doing a two-tailed test, okay, we're going to have two critical values. Okay? And if our test statistic falls in either tail, so if it falls over here or if it falls over here, then we reject the null hypothesis. So that's what that one with the absolute value was saying too. It was just a little, to me, it's a little more confusing written with the absolute value. Okay? So the formula for t-test statistics not too tough, but the one thing we might need to practice a little bit is being able to come up with our critical t value. So let's refresh our memory on using the t-table here. Okay. This one says find the critical t-score that corresponds with 14 degrees of freedom at the 0.025 level of significance for a right-tailed hypothesis test. Okay, so it already gives us degrees of freedom. We don't have to subtract on this one. Okay, if it gave us the sample size, we would subtract 1 to get our degrees of freedom. We don't have to do that here. And then we look at what type of test we're doing. It says it's a right-tailed test. So a right-tailed test means we only have one tail. And it gives us this 0.025 level of significance. That is the area in the tail. So we want 0.025 in one tail with 14 degrees of freedom. Okay, so if we go to our t-table, we would look for 0.025 in one tail with 14 degrees of freedom. So our critical t value is going to be 2.145. Okay? And since it's a right-tailed test, it'll be positive 2.145. If it was a left-tailed test, remember the t values on the left side are negative, so if it was a left-tailed test, it would be negative 2.145. And then if you're doing a two-tailed test, you've got plus or minus whatever t value you find on the table. So you'll have one on the positive side and one on the negative side. Okay? All right, so let's do a hypothesis test. We're ready. Okay? Let's look at this one. This one's a little wordy, but we'll get through it. It says, nurses in a large teaching hospital have complained for many years that they are overworked and understaffed. The consensus among the nursing staff is that the mean number of patients per nurse each shift is at least 8. That's the nurse's claim there. In order to prove their point to the nursing staff, the administrators gather information from a simple random sample of 19 nurses' shifts. The sample mean is 7.5 patients per nurse with a standard deviation of 1.1 patients per nurse. We want to test the administrator's claim using an alpha of 0.025 and assume that the number of patients per nurse has a normal distribution. This one's not worded all that well, but it does tell us to test the administrator's claim. So what are they saying? We can assume it's the opposite of the nurse's claim, right? The nurses say that the mean number of patients is at least 8. So we can assume the administrators are going to say that the mean number of patients is less than 8. Right? So our alternative hypothesis here, the administrator's claim would be that the mean is less than 8 patients. And that's the administrator's claim. Now the nurses, their claim turns out to be the null hypothesis, that the mean is greater than or equal to 8. That would be at least 8. Then we want to do our alternative hypothesis. We want to do our hypothesis test here to decide which claim carries more weight. Right? So if we look through the numbers we're given, okay, we need, looking back at our formula, we need mu, we need x bar, we need n, and we need sample standard deviation here, s, because nowhere in the problem does it give us the population standard deviation. So If it doesn't specifically say the population standard deviation is this, then the number we're given is going to be sample standard deviation. Okay? So the easiest number to start with to me is mu. That's the number from the hypotheses, 8. And if we look at what our data tells us, it says a simple random sample of 19 nurses' shifts, so that's N. The sample mean is 7.5 patients, so X bar 7.5. And then from this sample data, it says with a standard deviation of 1.1 patients per nurse. So that is our sample standard deviation, S. Okay, so now we can calculate our test statistic. Okay, so to get our t-test statistic, 7.5 minus 8 over, what was it, 1.1 over the square root of 19. And since we're dealing with t's and on our t-table we have 3 decimal places, we can round this to 3 decimal places. So our t-test statistic, negative 1.981. Okay. Now the other thing we need to figure out here, we're not going to figure out a p-value. We need to figure out our critical t-value that tells us where our rejection region begins. So to get a critical t, and we need degrees of freedom, and we need the area in the tail or tails. Okay. So looking back at our problem, N was 19. So to get degrees of freedom, 19 minus 1 equals 18. Now our area in the tails is 0.025. We got to decide if that's in one tail or two tails. So what type of test are we doing? This is a left-tailed test. So this is a one-tailed test. So we're going to look up 18 degrees of freedom with 0.025 area in one tail. And if you go to the t-table and you look that up, 18 degrees of freedom, 0.025 in one tail. Our critical t-value, 2.101. This is a left-tail test, so what else do we have to remember about our test statistic? Sorry, here, let's see. Since it's on the left side, our test statistic is going to be negative. Okay. And then you can either think about the picture or think about the rule. To reject the null hypothesis, what's got to happen? Well, the left-tailed test, so our test statistic needs to be more to the left or less than our critical t-value in order to reject the null hypothesis. So our rules would say that t needs to be less than or equal to our critical t. But here, if we look at it, negative 1.98, that is not less than negative 2.101. So we would fail to reject the null hypothesis. Okay, that's our conclusion here. Let's look at one more. Okay. So that was one-tailed. Here's the picture of what's going on. In order to reject the null hypothesis, our test statistic would have to be over here. But it's not, it's over here, outside the rejection region, so we fail to reject the null hypothesis on this one. Okay. Look at one more here. Let's do a two-tailed. Okay. This one says the meat packing department of a large grocery store packs ground beef in 2-pound portions. Supervisors are concerned that their machine is no longer packaging the beef to the required specifications. To test the claim that the mean weight of ground beef portions is not 2 pounds, the supervisors calculate the mean weight for a simple random sample of 20 packages of beef. The sample mean is 2.1 pounds with a standard deviation of 0.33 pounds. Is there sufficient evidence at the 0.01 level of significance to show that the machine is not working properly? Assume the weights are normally distributed. So the claim we're testing here is that the machine is not working properly. Okay. if it's not working properly, what's it supposed to be doing? It's supposed to be putting 2 pounds of beef in each package. So if it's not working properly, that would mean that the mean in each package is not 2. Okay? It doesn't specify it thinks it's putting too much or too less. We're just testing to see if it's not working properly. And so it should not equal 2. So our null hypothesis is that the mean does equal 2. Alright. And then next thing we can do is calculate our test statistic. Okay, so we need mu x bar s and n. Mu comes from the hypotheses. That's 2. It says the sample mean is 2.1 pounds, so that's x bar. Okay. And it tells us this sample had a standard deviation of 0.33 pounds, so that's our sample standard deviation, S. And then we'll have to look back as they calculated the mean weight for a simple random sample of 20 packages of beef. That's not big enough for the central limit theorem, but what else does it say? It says assume the weights are normally distributed, so that gives us the central limit theorem to be able to do our test here. Okay, so now we make our calculation to get our t-test statistic. 2.10 minus 2 divided by our standard deviation of 0.33 over the square root of our sample size, which was 20. We're going to round to 3 decimal places again. So on this one, we get a test statistic of 1.355. Okay. So now we need to find our critical t. And since it's two-tailed, we got half of our area in each tail, so the subscript is alpha over 2. That's not really super important. Okay. As long as you realize it's two-tailed. So it's two-tailed test. This is two-tailed. So this significance level, 0.01, is going to be in 2 tails. And then what about degrees of freedom? That's the sample size minus 1, so 20 minus 1. We've got 19 degrees of freedom. So we'll go to our critical t table. 19 degrees of freedom, 0.01 in 2 tails. That will give us critical t value, 2.861. And if we're being really specific here, since it's two-tailed, we've got positive and a negative version there because it's two-tailed. If we think about the picture, well, since our test statistic is positive, it's over on the right side, 1.355, so that would have to be further to the right than our critical t value, 2.861. It's not. It's somewhere in the middle. Okay, so the picture of what's happening here, we've got our curve, we've got our critical t's on here, we've got negative 2.861, positive 2.861, and our test statistic is somewhere right here in the middle, 1.355. Okay, so we don't get to reject the null hypothesis because these are the rejection regions in the tails. But our test statistic doesn't fall in the tails, it falls right in the middle of the curve. So our conclusion here, again, is that we fail to reject the null hypothesis. So not all that much different from section 10.2, we're just using rejection regions instead of p-values here.